Welcome to Calculus Lesson 6.2, Addition and Subtraction of Vectors. So the first thing we need to look at are some definitions. The first definition being resultant. Okay, so if you took physics with me, you would have heard this word many times. And if you haven't, that's fine. Resultant just means the sum of vectors. Okay, so if you take a sum of vectors, that means you have to add at least two different vectors together, or even the same vector. Okay, so the resultant turns out to be a single vector you obtain when you add 2 plus 2 or more vectors. Okay, and we'll see some examples of that. All right, zero vector. The zero vector is symbolized like this. You've got the number 0 with the vector symbol on top. So if you remember from lesson 6.1, we put this little arrow symbol to denote that you have a vector. If you don't put the arrow symbol, it means that this is just the number 0, not the zero vector. There's a big difference. Okay, so if you add multiple vectors together and you end up exactly where you start, that means you haven't moved anywhere from where you started. Your displacement is 0. Okay, so the zero vector, this is a vector with magnitude 0 and no direction. Okay, remember what a vector is. A vector is a quantity that has both magnitude and direction. So if you don't have a magnitude, imagine an arrow that has no length. It can't point anywhere. So we're going to move into example 1. Okay, so example 1, we're going to look at some vectors. So consider these two vectors. I've got here vector u and I've got vector v. They're different lengths and they're pointing in different directions. Okay, so part A. Find u plus v. All right, so that's not so bad. Remember, you always add vectors tip to tail. And what that means is the tail of one vector gets attached to the tip of the other. So now you know addition is commutative. It doesn't matter if I do u plus v or v plus u, it has to give me the same result. The overall picture might look a little different, but the resultant vector is going to look the same. Okay, so let's do this. So I'm going to sketch u first. So u has about this length that's going down and to the right. Now I have to add v to that. So onto the tip of u, I'm going to attach the tail of v. So I have to draw a vector with this magnitude going in this direction on the end here of u. So it's going to look something like this. So there's v. All right, now the sum vector. The sum vector, always pay attention to what I'm going to say here. The sum you always draw from the tail of the first vector to the tip of the final vector. Now, you might have 2 vectors you're adding. You might have 3. You might have 5. Okay? From the tail of the first vector to the tip of the final vector. So I'm going to draw my resultant in like this. Okay, so that's the vector u plus v. And now that is its own new vector. You can call that w if you want, but that's how it looks. And that is the resultant. Okay, notice it has its own magnitude, it has its own direction. We will do some problems where we actually have to figure out the exact direction, how to quote it, as well as what the actual magnitude is going to be. So we'll get to that. All right, so that is adding vectors. Now, what if you were asked to subtract the vectors? So find u minus v. All right, well, I'm going to tell you something. When you subtract vectors, instead of learning a whole new rule, what I'm going to say is, when you see a subtraction of vectors, imagine you're adding the negative. So I have u minus v. That is the same thing as u plus negative v. Okay, so why is that important? Well, like this, I'm adding vectors together, and I know how to add vectors. I add them tip to tail, okay, and I did that right here. Don't worry about the fact that there's a minus here. This is just a different vector. In fact, negative v, this is the opposite vector of v. Now, if you remember from lesson 6.1, I defined what an opposite vector was. An opposite vector has the same magnitude, and it's going in the opposite direction. Okay, so let's take a look. V is up here. Okay, so V has a certain length. It's going to have the same length, but it's going to go in the exact opposite direction. So instead of going right and slightly down, it's going to go left and slightly up. Okay, so that means negative V looks something like this, since V looks something like this. All right, so I'm going to add this vector with U. All right, so using the same strategy I had before, let's sketch U in first. So U looks something like this. Okay, now add to that negative V. Okay, so if I put negative V, so that's something like that, I'm going to have to add these two vectors. Okay, so in retrospect, I should have probably written the U on this side. All right, so, well, anyways, it's done. Let's do the sum here. So from the tail of the first vector, okay, tail of the first vector to tip of the final vector. Okay, same process. So now that's U plus negative V. Also known as U minus V. And so we can see that that magnitude is quite a bit shorter than the U plus V, and it's going in a different direction. All right, so that's just some introduction to this kind of stuff here. So let's move on to another example. All right, example 2. All right, so I'm going to sketch here a parallelogram. Excuse me. Okay, and this parallelogram has vertices H, E, F, and G. I'm going to draw some diagonals in here as well. Now that point in the middle, I'm going to call that J. And I'm also going to just show here that, okay, these two sides are parallel. That's what these arrows mean. Okay, so those arrows are not meant to represent a vector. These are just lines. Okay, the fact that I have these arrows just means that these two sides are parallel and these two sides are parallel. Okay, so again, not meant to represent a vector. So now given this picture, part A, express HF as a sum of two vectors. Okay, so first identify where HF is. HF is from here to here. You know, the fact that I have an arrow on top, that's telling me that I'm dealing with a vector here. All right, so what I'm looking at is the vector that's starting from H and going to F. Now, even though I don't have it in the picture, what I want to visualize is an arrow whose tail is at H and whose arrowhead is at F. So that little tip, that little arrowhead is right there at F. All right, so we have to express it as a sum of two vectors. Now, if you just visualize HF is going to look something like this. So that's your vector HF. We have to figure out two vectors that add up to it. Now, there are going to be a lot of different possibilities here. Okay, so for example, HF, how do we get from H to F? Two vectors, tip to tail. Well, I can start at H, go to E. Okay, so I've got the vector HE, and then added to that, I can add EF. Right? Because if I have HE and I add on to that EF, so here's EF. This one here is HE. Well, guess what? When I add those two vectors, tip to tail, right? So from the tail of the first vector to the tip of the final vector is my sum. That's going to be HF. And that is exactly what I'm looking for. Okay, so HE plus EF, that's HF. So that is one possible answer. So HF is equal to HE plus EF. And that's really all it is. You just have to come up with different combinations that'll give you the correct expressions here. All right. So that's one. I can also go from H to F by going from H to G and then from G to F. Okay, so that's another possibility. HG plus GF. Remember to always put the arrow. If you don't put the arrow, it means you're dealing with a line segment, so that would not be correct. All right, let's see, what else can I do? Well, so I've got, I can actually do an even more direct route. You know, I didn't even think of this. I can go from H to J and then from J to F. So HJ plus JF. And you can probably see now there's so many possible options here. But there are some options that may not be so obvious. I mean, these ones were already connected. I mean, you have HE and then E is already connected to E, so you have EF, and then you have HG and GF. This is not necessarily how it has to be. These middle letters don't have to match. Okay, so remember that from 6.1, if you have two vectors that are equivalent, that means they have the same magnitude and they're going in the same direction. They don't have to be in the same spot in space. Okay, so for example, if I look at this picture, I can see that EF is going right and it has a certain length. I know that HG has the same length and it's also going in the same direction. These two are parallel, right? So EF is equivalent to HG. So what that means is I can take that first expression, HE plus EF, and change it to HE plus, well, like I said, EF is equivalent to HG. So HE plus HG. That's another possible answer. Okay, so what else can we do here? Well, we have to get to this point. So we need one vector going up and we need one vector going right. Well, I don't always have to start at H, right? I don't have to go HE plus EF or HE and then something else. I can replace HE with something else. Okay, so HE has a certain length, it's going in a certain direction, and the only other vector that has that length and going in that direction is GF. So I can replace HE with GF. So every instance where I see HE, I can replace it with GF and just add the rest. So I can do, if I have HE plus EF, I can do GF plus EF. I can even take the example that we just did, HE plus HG. I can do, let's see here, I can do GF plus HG. So that also works here. Now just look at the picture, all right? So if I have GF, GF is going like this, right? So I have a vector that's coming up like that. Now HG is a vector that's going right, and it also has a certain length. You take the tail of that and you attach it to the tip of this vector. It's going to go like that. And sure enough, the resultant is exactly what you want, HF. Okay, so again, it doesn't matter where it is in space as long as the magnitude and the direction are the same. That makes two vectors equivalent. And believe me, there are many, many, many more answers here. We're not going to go through them all. All right, so hopefully that gives you a good idea. That's the sum. Now, the not so fun part, but still not too bad, the difference. Express, let's see, express FH as a difference of two other vectors. All right, difference meaning subtraction. Okay, so the way I want you to think about this is that subtraction of vectors is just like addition, okay? Just you're adding the negative instead of adding the positive. So FH, first of all, let's see where FH is. FH is starting in the top right, going to the bottom left. So I have an arrow going kind of like this. So there's FH. Okay, so let's look at this from the perspective of addition first. If I was trying to figure out two vectors to add to get FH, I could do FE plus EH. All right, so let's just write that down for a moment. FH would equal FE plus EH. Now, subtraction is just adding the negative, right? So if I have vector EH, well, I'm going to change that into its opposite vector. Okay, so let's take a look at the picture again just for a moment. EH has a certain length, right? And it's going to the right. So let me just resketch vector EF down here. Okay, so EF looks like this. Hopefully that's okay. It's going to the right. It has about this length. So if that's EF, well, that means the opposite vector, FE, would have the same magnitude and it would go in the opposite direction. So this would be FE. Now, something that students saw in physics class, and if you haven't taken physics, that's fine, is that sometimes we can quote directions as opposite directions. So for example, if I said to you, walk 5 meters west, well, you would walk 5 meters west. If I told you walk 3 meters in the negative south direction, right? Negative south, almost everyone always tells me, well, negative south, that must mean north. And sure enough, that's what it is. If I tell you negative of a direction, that means you're going in the opposite direction. So if EF and FE are indeed opposite vectors, that means EF is equal to negative FE, right? I already know FE is in the opposite direction to EF, so if I put a minus in front, that puts it back in the correct direction, right? So negating a negative makes it a positive again. All right, so why am I doing all of this? All right, so I was working with FE here, but it could work with EH as well, right? So if that's the case, now I can also say, well, due to that, EH is equal to negative HE. And I can do this with any vectors I want. If I have AB, it's equal to negative BA. I don't even need to see what the picture looks like. That's just going to be a natural consequence. Okay, so if I have EH is equal to negative HE, well, guess what? Look here. I've got FE plus EH. If EH is the same as negative HE, well, I'm going to replace that. So FH is equal to FE minus HE. Now, if that was too big a step for you, imagine it was FE plus negative HE, right? Because we replaced the EH with negative HE. So hopefully that's okay. And then from that, you get this expression. All right, so that's how we can come up with a subtraction fairly easy, just using sum of vectors. Okay, let's just do 2 more, okay, just so you get the idea. Okay, so we're going to continue this over here with another example. So we've got FH, right? So remember FH is like this, right? So from F all the way down to H. So we're actually going to express that as now FG plus GH, okay? FG plus GH, okay, and that's equal to FH. Okay, so I'm adding them. This is the same thing as having FG minus HG. Okay, same thing, so that's another possibility. Okay, we'll do one more. Of course, just like the addition, there are so many examples, but we're not going to go through all of them. The point is just for you to see that there are many different kinds. Okay, let's do one more. So we've got FH again that we're looking for. So let's see, what can we do here? Let's see. If we do FE, and we still have to come down, so instead of EH, why don't we do FG? Okay, so FE plus FG. FG is still going down, so if I attach that vector here, that's equivalent to EH, I get the same destination, FH. All right, so that means what I have here is FE plus FG. Okay, now again, we're going to get the opposite vector here, so instead of FG, I'm going to have GF. But I know that FG is equivalent to negative GF. That's going to be my connection here. All right, so FE plus negative GF, which is the same thing as FE minus GF. So that's my third option there. Okay, so I've got this, and I've got this, all 3 of those. Okay. So again, this was a non-numerical example, but now you have a better idea of how to add vectors. The last example I want to do will actually involve numerical values. Okay, so something that you learned back in grade 11 math, sine law, cosine law, all going to come back here. If you're in physics, this is going to be review, hopefully, for you. So here we go. Okay, so example 3. Now, of course, we can always add context to this kind of example. I'm not really going to waste your time with the context. If you get the question with context, like Susan needs to buy ice cream and she's going to the store and she walks 100 meters east and then she turns north 70 degrees east and she walks 60 meters, what's her overall displacement? You can always add something. Or maybe Sean has to return a library book. Again, I'm not going to bore you with the details. So this person is walking 100 meters east. So again, based on 6.1, I said always put directions in square brackets. So this is east. So the person walks 100 meters east, and then they walk 60 meters at this direction. Starting at north, you move 70 degrees toward the east, and I want to know what is the overall displacement. So really what you have here is you have two vectors, and looking for the overall displacement, you're looking to find the resultant. Okay, that's what you're looking for here. So first thing I like to do in these kinds of problems is figure out where my resultant's going to be. I just kind of try to visualize it on the paper so I know where to start drawing. Do I start in the top right, or sorry, top left, bottom right, top right, bottom right, wherever. Okay, so I'm moving 100 meters east, so I'm going this way first. And then I go north 70 degrees east. So then I'm going up and to the right. So I don't want to start my drawing up here because then I'm going to have to draw into the words. So I'm going to start my drawing down here. So what I like to do is draw a mini Cartesian coordinate system, also known as just a little plus sign. Okay, my first vector is going, well, it's going east. All right, so grab your ruler. My first vector is going east, and it's going 100 meters. This doesn't have to be to scale, but try to keep it, more or less accurate. So there's 100 meters. Now, when you're finished drawing your first vector, always draw another Cartesian coordinate system. Okay, so something like that. So the second vector I add to the tip of the first. So the tail of the second goes to the tip of the first. It's 60 meters, okay, north 70 degrees east. So north is like this. Okay, always draw a compass. You at least have to identify the north direction. So north 70 degrees east, 70 is more than the 45 point. So 70 degrees will be something like this. And I just want to draw my arrow a little bit shorter than the 100 meters. So maybe something like that. Okay, so that's 60 meters. I'm going to fill in the 70 with this because, well, this marker is quite thick. Okay. Now my resultant is going from the tail of the first vector to the tip of the final vector, just like before. So here I go. I'm going to connect my ruler here. Again, arrow goes from the tail of the first vector to the tip of the final vector. Okay. So what I have to do is I have to find this. So if I call displacement delta D with an arrow on top, this is delta D with the arrow on top. I got to find that side. Now that I have the picture, I kind of understand what I'm dealing with. I take this and I redraw the triangle. Okay, so we're just going to quickly redraw it here. Let me just keep the question in there. So I just like to do a quick sketch. So my triangle looks something like this. Now this side is 60, this side is 100. The units are the same. That's what I really care about here. I've got a 70-degree angle here. I'm trying to figure out what this big angle is. So if you notice that this angle on the left, that's 90 degrees. The angle between north and west is 90 degrees. So 90 plus 70, what's that? That's 160 degrees. So 160. So the reason I do this is because now I start to, well, label my triangle. Okay, so what I'm going to do here is label this. So the corners get capital letters, so let's say A, B, and C, and the corresponding opposite sides get the respective lowercase letters. So little c is 100, little a is 60, and we are looking for little b. Okay, so what you have here is a side angle, side. If you remember that from grade 11 math, that means we have to use cosine law. All right, cosine law, it's kind of like an extension of Pythagorean theorem, so you have to just remember that formula. So the formula is b squared is equal to a squared plus c squared minus 2ac times cosine of capital B. This angle, this side must have the same opposite letter. Okay, so if this was A, this would be capital A. Since this is B, this is capital B. All right, so fill in your values. So A is 60, C is 100, minus 2 times 60 times 100 times cosine of 160 degrees. Make sure your calculator is in degrees. So usually in calculus, in math, your calculator's in radians. Okay, so sometimes you're going to be in degrees. Always watch out for that. So here we go. Grab your calculator. Again, make sure it's in degrees. So mine is. I've got the D on the top there. 60 squared plus 100 squared. If you're going to enter it in your calculator all at once, by the way, make sure you are being very careful using brackets religiously. So minus 2 times 60 times 100 times cosine of 160. All right, so we get some kind of value there. Now remember, that's b squared. So if you square root that, we're going to get 157.7 approximately. So b is approximately 157.7 meters. If you're wondering how many values to give this to, well, if you were in IB math, this would be 3 sig figs, so 158. This is the ministry knowledge, so if you want to give it to 1 decimal place, it's fine. If you want to round it to 158, that's fine, okay? Just round it to a reasonable number of significant figures or digits, okay? So I've got the magnitude. Vector has a direction as well, though, right? So I got to figure out which way that vector is going. Now, if you look at the original picture, if I could just figure out what this angle here is, right? So let's call that alpha. If I could figure out what alpha is, I could say that, well, the resultant displacement, okay, is 157.7 meters at alpha degrees. So starting at east, alpha degrees towards the north, right? East and then heading up towards north. So, well, how do I find that angle? In this problem, it's a bit easy because that angle is just angle A. So if I find A, I've got alpha. Sometimes you might have to do a few more steps to figure out what the angle is, but it's just a series of logical, geometrical problem solving. So I'm going to look for A here. All right, so here we go. Since I'm looking for an angle and I have the opposite side, and now I have another side angle pair, I'm going to use sine law. So sine of A over A is equal to sine of B over B. Now, usually I frown upon this and I say don't use information that you just calculated to find something else. But in this case, your hands are kind of tied. So looking for sine A, so that's going to be A over B times sine of B, right? It's all just multiplication and division. It's commutative. Okay, so here we go. So A is 60, B is 157.7 times sine of 160. Remember, that's sine of A. Okay, so 60 divided by 157.7 times sine of 160. Okay, so of course that's going to be some small number. Take the inverse sine of that, and we have about 7.5 degrees. I'll call that 7.5. Okay, so that's 7.5 degrees. That's starting from east, so you could say that your angle is east, 7.5 degrees north, and it makes sense according to the picture. Okay, or you could say north, and then 90 minus 7.5 towards the east. Now, usually with these directions, so if you remember 6.1, we said that there were 2 ways to give directions. There was a true bearing, also known as azimuth bearing, and there is quadrant bearing. So with the quadrant bearing, you always start from either north or south. So that means I'm going to want to start from north in this case. So if I want to start from north, so actually let me just come back up to the picture here. Oops. So if it's east 7.5 degrees towards the north, then it's going to be 90 minus 7.5, which is 82.5 degrees if you start from north and you go east. So this angle here is 82.5 degrees. That's what we're going to use. All right, so we're done. So therefore, my displacement, which I've just called delta D here, is equal to about, I'm going to round this off, just make it look nicer, about 158 meters north 82.5, okay, we'll keep it as 82.5 degrees east. If you want to make that 83 degrees, that's fine. There's our final answer. Okay, so final answer, this is the resultant. It's a single vector, magnitude, unit, correct direction. Okay, so that is it for this video 6.2. Okay, so stay tuned next time for video 6.3.